Hello everyone. This is the first of our online lectures, and I wanted to try to refresh our memories with chapter 8 where we left off long ago before spring break, and so it may be a little bit dusty in all of our minds. So I wanted to go back and review a lot of the things we discussed before the break. We were discussing chapter 8, which is all about rotational motion, and the first thing we talked about was the difference between rotational or angular speed and linear speed or tangential speed. Basically, we thought about an example of, say, a spinning disc, and looking at the rate at which the disc spins, it would have the same rotational speed throughout, but the tangential speed or linear speed is going to depend where on that disc you actually are located. So the angular speed or the rotational speed is essentially the time rate of change of your angular position over time. Whereas the linear speed is the same sort of speed that we discussed before, distance divided by time. And the way that those two things would be related to each other, for example, on this merry-go-round or turntable example, is that the linear speed would be proportional to the rotational speed, and the constant of proportionality then would be your distance from the center of the rotation or the rotational axis, R. Okay. We also talked about this idea of rotational inertia. When we studied inertia back when we were discussing Newton's laws, we talked about it in terms of a resistance to the motion being changed. And so rotational inertia is analogous to this. It's sort of a resistance to being rotated. And the larger the rotational inertia is, then the more difficult it will be to rotate. When we discussed Newton's laws and inertia initially, we thought about it in terms of the mass of the object. For rotational inertia, we said that it not only depends upon the mass, but it also depends upon how the mass is distributed with respect to the rotational axis. And we passed around some long rods through the class. One was red and one was blue. Hopefully all of you had a chance to experiment with these. I think it was the last demo we got to do this semester, but we demonstrated that they were the same mass by weighing them, but then when you actually try to rotate them about the center, you should have found that the red one was much more difficult to rotate than the blue one, and that had to do with the fact that the mass, while it was the same amount, was distributed closer to the ends, or in other words, farther away from the rotational axis compared to the blue. Okay? And so when we say harder to rotate, what do we actually mean? The idea here is that whenever we're trying to accomplish some sort of rotation, yes, we have to apply a force, but more specifically, we have to apply something that we call a torque. And the torque depends upon the force that you apply, but it also depends upon how that force is directed. And what we mean by that is that it's the force times the lever arm, and it also matters what angle you apply the force. So the example pictures that I showed you were of a wrench, and you can see in each picture in the first example, the force is not being applied perpendicular to the lever arm. So that's going to achieve less torque than if I align the force so that it is perpendicular to the lever arm here. And I can achieve even more force if I make the lever arm longer. More torque if I make the lever arm longer. Okay. And then we did a quick example where we took the case that you were applying the force at a 90-degree angle or perpendicular to the lever arm, and that force was equal to 200 newtons, and the lever arm was half a meter. And when we found the torque, we decided that it was 100 Newton meters. Finally, that example was just for a single torque. An object may be subject to more than one torque, and if we wanted to examine what the net torque was, we would have to consider the direction of each force being applied and the lever arm and the amount of force that's being applied, and we could add all of these things up, taking care to mind whether or not it was a positive or negative torque. And if all of those torques add up to 0, then the object is said to be in rotational equilibrium. So a quick example of something like that would be if you had some sort of a balance scale and you had some object on one side of the scale providing a force by virtue of its weight times the lever arm, where this would be your lever arm from where the object is located to this rotational axis at which the thing could pivot. And then if you got a value here that was, say, 200 Newton meters, and then you put some weights here to compare it to, and they had a certain force times a lever arm, and this was also equal to 200 Newton meters. This force is directed this way, which would produce, if it was on its own, it would produce rotation in a counterclockwise sense. This torque is directed the opposite way, so it would produce clockwise rotation if it were the only thing on the scale. And so these two torques are opposing one another, which means that they effectively cancel one another out, and you have a net torque equal to 0, and this thing then should not rotate. It will be in rotational equilibrium. Okay, and then the last thing that we discussed before the break was a concept called centripetal force, and this was the idea that something has to keep an object rotating in circular motion, so that something is some sort of centripetal force. It could be provided in different ways. If you were whirling something on the end of a string overhead, then the force of tension would be the thing providing the centripetal force. Another example would be a planet orbiting a star, in which case the force of gravity provides the centripetal force. And what we discussed was that the centripetal force, if we think about it mathematically, it's going to be equal to mv squared over r, where r is the distance to the center of rotation. So we discussed an example of a car going around a bend, and the r in this case would be the distance to the center of curvature, and the centripetal force would be provided by the force of friction on the road, and sometimes that's also aided by a slant in the road that provides an additional way of achieving centripetal force. But if we just think about it on a flat surface in terms of the friction, then we can think about how the centripetal force plays out here. And when we did our clicker question, we decided that if we wanted to go crazy and double the speed around a certain bend, that would require 4 times the centripetal force, because the velocity gets squared there. And so you would really be relying on friction a lot just by doubling your speed. So you want to take care around sharp bends, was the upshot. Okay, and that was where we left off last time with all of the rotational stuff. And so I wanted to move on and discuss, when I mention centripetal force, a lot of times this conjures up ideas in people's head about this centrifugal force, as people call it. This is actually not a force in the truest sense of the word, in the sense that you really require to be looking at an accelerating system in order for it to be considered a real force. It's something that people tend to think of as being real because it feels as though you are being pushed out against the side of something that is rotating. If you think about it, though, really what's holding you in that rotation is the centripetal force pulling you inward. And if, for example, the string would break on the can that you're whirling overhead, you would just continue tangentially on a path there, like is indicated here. So if there really is centrifugal force, that would imply that you would be heading outward rather than tangential. In order to see the centrifugal force, you have to be thinking about an accelerating frame of reference that is sort of moving along with the object that is in motion. In other words, a rotating frame of reference. And in that case, you could think about it as a force. And in fact, we can achieve some sort of simulated gravity by rotating things in a space station, as you might have seen in different sci-fi films, by exploiting this idea. Okay, so the final thing that we need to discuss in Chapter 8 is angular momentum. So angular momentum is the rotational analog to linear momentum. And if you can think back to what we discussed with linear momentum was the mass times the velocity. And so if we wanted to produce an angular analog to this, the naive thing you might do is take the rotational analog to mass and the rotational analog to velocity and multiply those two things together. And if you would suspect that that's what you would get for angular momentum, you would be right. So we are just going to take rotational inertia, since that's analogous to mass, times rotational velocity or angular velocity to find the angular momentum. And so an important thing to know about angular momentum is that angular momentum, like linear momentum, is a conserved quantity. We had the law of conservation of linear momentum, and likewise we're going to have a law of conservation of angular momentum, which basically says that as long as there are no net external torques, then the initial angular momentum should equal the final angular momentum. And this condition is also analogous to conservation of linear momentum, because what was required for linear momentum to be conserved was that there was no net external forces. So in the rotational picture, torque is analogous to force. That's why we require that there's no net external torques for angular momentum to be conserved. Or that's one way of thinking about it, at least. So what this is basically saying, though, is if I change, for example, my rotational inertia, then that will change my speed in the final state, so that the product of the rotational inertia times the angular speed will stay the same. So the classic example of this is an ice skater who may start out with a large rotational inertia by extending her arms, or as this cartoon portrays, a person standing on a rotating platform holding dumbbells extended on each arm. And just like that red rod that we were discussing, this mass is now distributed far away from the rotational axis, and it's going to be more difficult to rotate. So the rotational inertia is high for this kind of setup. And so if you start spinning like this, and then you bring the dumbbells in, or the ice skater brings her arms in while she's turning, now you've made your rotational inertia smaller, and because of the law of conservation of angular momentum, this will, as a consequence, speed your rotational velocity up. And you've all probably seen this with figure skaters as they bring their arms in and they become faster and faster in their spin. Okay, so that about wraps up Chapter 8. The summary of all the things we discussed can be seen right here. We've got the tangential speed being related to the angular speed by this equation here. We talked about torque as being force times the lever arm. We said that if the net torque on an object adds up to 0, then it's in rotational equilibrium. We discussed centripetal force as being mv squared over r. We talked about angular momentum, I times omega, and that the angular momentum should be conserved in the absence of net external torques. Okay, so that's about it for today. I will post another lecture soon, and take care.